Semiconductors is currently at the heart of the worldwide rise in technological nationalism and Cold War. Projected to be a $1 trillion market by 2030, they are key to all solid-state devices, which underpins the modern-day and future economy. Scanning through the periodic table, the D and S block elements are mostly metals in its most general sense. This includes alkali and alkaline metals, transition metals, rare earth metals, etc. The P elements, on the other hand, are dominated by reactive nonmetals and noble gases. Smacked right in the middle between the D and P elements, there we find the only 3D elemental semiconductors. They are the well-known group 4 elemental semiconductors, silicon and germanium. Before we talk more about them, let's first define what is a semiconductor. Or first, what is a metal? A metal is a material where the Fermi energy is located within a band or bands of electronic states, where states below or above the Fermi energy are filled with electrons. Such partially filled bands is the reason why a metal conducts electricity. A semimetal is like a metal, but whose bands has smaller density of states, thus much smaller electron density. For example, metal has about 1 electron per atom, whereas semimetal typically has 1 electron per 100 atoms. An insulator, on the other hand, consists of band or bands of filled states separated from the empty states by a band gap. As the name implies, a band gap is an energy window with the absence of any electronic states. Although the Fermi energy is located within the band gap, the gap is so large no electrons can be thermally excited into the bands. Hence, it does not conduct electricity. A semiconductor, as the name implies, is in between a semimetal and insulator. However, its band gap is smaller. It is small enough where free electron or hole carriers can be thermally excited across the band gap. By convention, we call the band of unfilled states the conduction band, and the filled states the valence band. Here, EC and EV denotes the energies of the conduction and valence band edges. The energy difference between EC and EV defines the energy gap, e.g., how small is the band gap to be qualified as a semiconductor? As we shall see later, that very much depends on applications. The elemental semiconductor germanium has an energy gap of 0.67 electron volts. It is lustrous, hard brittle, and grayish-white. It has an atomic number of 32 and belongs to group 4 of the periodic table. Thus, it has 4 electrons in the outermost shell. We call them the valence electrons, and these are the electrons that make up the valence band. Since its energy gap coincides with that of the infrared electromagnetic spectrum, germanium is used to make infrared optical components to absorb and emit infrared light. For example, one can find these germanium optoelectronic devices in night vision goggles, thermal imagers, and infrared astronomy. Germanium is also used in high-performance integrated photodetectors for silicon photonics, since silicon photonics operates in the infrared at 0.8 electron volts. Due to its high electron mobility, germanium is also an excellent material for high-speed heterojunction bipolar transistor used in high-frequency microwave operation. Most notably, the first transistor ever assembled was invented in Bell Labs in 1947. At that time, it was called a point contact transistor, as the structure consists of a gold wedge making electrical point contact with the semiconductor, which is germanium. This pioneering work was performed by William Shockley, John Bardeen, and Walter Brattain. They were jointly awarded the 1956 Nobel Prize in Physics for their researches on semiconductors and their discovery of the transistor effect. However, for practical reasons, such as the abundance of silicon and its innate ability to high-quality thermal oxides, the silicon metal oxide semiconductor field effect transistor, or MOSFET, replaced germanium to be the semiconductor of choice for integrated electronic circuits. Like germanium, silicon is also a group 4 elemental semiconductor. However, it has a smaller atomic number of 14. Thus, electrons are more tightly bound to the nucleus. Thus, it has a larger energy gap of 1.1 electron volts. Today, the semiconductor chip giants, such as Intel and TSMC, can pack tens of billions of transistors onto a single silicon chip, leading to more than 10 million-fold enhancement in computing performance over the last 3 decades. Out of Bell Labs also came the first practical silicon solar cell, or the photovoltaic device which converts light into electrical energy. Over the last decade, solar photovoltaic global installed capacity has increased tenfold. One of the reasons why silicon stands out as the prime semiconductor material for many key industries is its natural abundance. Silicon makes up 27.7% of the Earth's crust by mass and is the second most abundant element, next to oxygen. But silicon cannot solve all problems. For example, electric vehicle charging would require high-power electronics. To sustain these high voltages, these transistors require semiconductors with a band gap much larger than 1 electron volts. Here, diamond, which has a band gap of 5.47 electron volts, would be ideal. It is an elemental semiconductor from the group 4 element carbon. Of course, in most applications, we would consider diamond to be an insulator instead. The use of diamond as a semiconductor for high-power electronics is a current topic of research which still faces difficult challenges due to its large band gap. If we only limit ourselves to the group 4 elemental semiconductors, then we don't really have many choices. Besides diamond, silicon, and germanium, tin also exhibit a naturally occurring semiconducting phase known as the alpha tin. However, its band gap is only 0.1 electron volts. Interestingly, these gap materials all have the same crystal structure just like diamond. Can we have semiconductors beyond these elemental group 4 semiconductors? To answer this question, let's examine the diamond crystal structure. As depicted, the unit cell has a cubic structure which belongs to the face-centered cubic Bravais lattice. Here, A is also the lattice constant of the crystal. Let's visualize the atom's configuration along different z-plane. For z equals 0, we have 4 atoms located at the corners, 1 in the center. At the next atomic plane at z equals to 1/4 of the lattice constant, we have 2 atoms, which are individually connected to the corner atoms in a diagonal manner. For the next atomic plane located at z equals to 1/2 of A, we have 4 atoms located at the centers of the cubic faces. At z equals to 3/4 of A, we have again 2 atoms along the diagonals of the cube. Finally, for z equals to A, where we have 4 corners atoms and 1 center atom, if we were to take these 4 blue atoms and replace with atoms from a different element, herein illustrated in red, then we form the so-called zinc blende structure. For example, silicon and carbon can form such zinc blende structure, producing a compound semiconductor known as silicon carbide, which has a band gap of 3.26 electron volts, intermediate of silicon and diamond. It is perfectly suited for power electronics, thanks above all to its ability to withstand high voltages due to its larger band gap. Compound semiconductors thus open a wealth of opportunities in materials science. Per the materials database, there are about 150,000 inorganic compound solid-state materials, of which 53% of these materials are either insulators or semiconductors. Before diving into the world of compound semiconductors, let's ask a very basic question. What is so special about the group 4 elements that makes it semiconducting? Let's start with the very basic entity of a single atom with only an s orbital electron. Bringing 2 such atoms close together will lead to the hybridization of the s orbitals, thereby forming new bonding anti-bonding states. The bonding state is lower in energy, while the anti-bonding has higher energy. Since each atom contributes 1 electron, there will be a total of 2 electrons, which will both occupy the bonding states. By extension, if we have 4 closely spaced atoms, then there will be a total of 4 hybridized states, 2 bonding and 2 anti-bonding, hereby denoted by blue and red respectively. The blue bonding states will all be occupied with electrons, while the red anti-bonding states are not occupied or empty of electrons. When we have a configuration where only half the states are occupied, we call it half-filling. If we have an extended chain of such atoms, then these discrete states would form a band of states which for most measure can be viewed as a continuum of states, herein denoted as S-band. It follows from our previous argument that the S-band is half-filled. The alkali metals, which has a valence electron of 1, fit this description here. These half-filled bands implies that electrons can be accelerated to higher energy with an applied electric field. Thus, they conduct electricity. If we have 2 electrons per atom instead, then the S-band will have to be completely filled. But a completely filled band cannot conduct electricity since there is no available states for electrons to move into. Clearly, this cannot be the case. As we know, the group 2 elements are known as alkaline metals. The complete physical band picture would require the consideration of the excited p orbitals. These p orbitals from neighboring atoms would also hybridize to form a band continuum. This p band, although unoccupied, overlaps in energy with the completely filled s band as shown. These overlapping p band states would therefore accommodate electronic conduction from electrons in the s band. This explains why electrons can conduct in group 2 alkaline metals, such as magnesium. Now, what about the group 4 elements, which gives us the semiconductor materials? Here we have 4 valence electrons, 2 in the s orbitals and 2 in the p orbitals. Supposedly, the hybridization of these orbitals with neighboring atoms would form the s and p band continuum. However, elements in this group like to form diamond-like structure, where the atoms are tetrahedrally bonded to the neighboring atoms. Since these bonds are equivalent, each of these bonds must be composed of a mixing of s and p orbitals. We call these sp3 bonding orbitals. For each bonding orbital, there is a counterpart sp3 anti-bonding orbital at higher energy. These 4 sp3 bonding orbitals are occupied, while the 4 sp3 anti-bonding orbitals are empty. The sp3 hybridization thus leads to a completely filled sp3 bonding band and a completely empty sp3 antibonding band. The hybridization also produces an energy gap that separates the sp3 bonding and antibonding bands as shown. Suppose n is the number of atoms. Then we went from a fully filled s band with 2 n states and a partially filled p band with 6 n states, to the completely filled sp3 bonding band with 4 n states and empty sp3 anti-bonding band with 4 n states. Thus, we have perfect half-filling, where all the 4 n valence electrons occupy the 4 n sp3 bonding states. We call the completely filled sp3 bonding band the valence band, since it is being occupied by all the valence electrons. The empty sp3 anti-bonding band is called the conduction band. The energy gap that separates the conduction and valence band is the band gap. Now we are ready to build up the picture from bottom up. When atoms are brought together, their neighboring discrete orbitals hybridize and began to merge into a band continuum. When the atoms are brought close enough, the s and p orbitals began to hybridize into sp3 orbitals to form the tetrahedral bonding configuration. The hybridization into the sp3 bonding and anti-bonding bands also open an energy gap like what observed in the alpha phase of TIM. The smaller atomic number or distance produces progressively larger band gaps, as observed for germanium, silicon, and carbon. Most importantly, the sp3 bonding band, or the valence band, is completely filled with electrons, while the anti-bonding conduction band is empty of electrons. Such half-filling arrangement of electrons is why we have these elemental semiconducting materials. Now the question is whether we can exploit the same physical principles we uncovered for the group 4 elemental semiconductors to the zinc blende compound semiconductors. How do we design the semiconductor so that we preserve the sp3 hybridized bands with exactly half filling? The design rule we are looking for is given by the so-called Grimm-Sommerfeld rule, which says that covalent compounds with an average of 4 valence electrons generally have tetrahedral structure mediated by sp3 hybridization. Let's see how the Grimm-Sommerfeld rule is being applied in practice. But first, let's quickly revisit the group 4 elements. The Aufbau principle states that electrons fill lower energy atomic orbitals before filling higher energy ones. The energy hierarchy of these atomic orbitals are provided by the path traced out by the blue arrows, going from low to high energy. With this, we can write down the electronic configurations of these group 4 elements, where we highlight in red the valence electrons in the outermost unfilled shell. They are 2 electrons in the s orbitals and 2 electrons in the p orbitals. Following Grimm-Sommerfeld rule, the intuitive combination of elements to ensure an average of 4 valence electrons would be to mix elements from the group 3 and group 5 of the periodic table. We can again use the Aufbau principle to enumerate the electronic configuration of each elements. Indeed, we see that elements from these 2 groups does provide an average of 2 valence electrons in the s orbitals and 2 electrons in the p orbitals. We can of course extend this idea further to the group 2 and 6 elements. Herein the group 2 elements consists of beryllium, magnesium, zinc, and cadmium, which all have 2 valence electrons in the s orbitals. Since the group 2 elements all have empty p orbitals in the next energy ladder, while the group 6 elements have 2 valence electrons in s orbitals and 4 in p orbitals. They on average also have 2 valence electrons in the s orbitals and 2 in the p orbitals. These group 3,5 and 2,6 compound semiconductors generally form a homologous series of compounds possessing the zinc blende or the hexagonal wurtzite crystal structure as shown. Just like the zinc blende structure, the wurtzite structure also consists of atoms in the tetragonal arrangement. A well-known 3,5 compound semiconductor is gallium arsenide. It is probably the second most used semiconductor after silicon. It has a higher saturated electron velocity and electron mobility compared to silicon. Thus, it is commonly used in high-speed digital and analog devices. Another important property of gallium arsenide is that it is a direct bandgap semiconductor. In other words, its conduction and valence band edges are located at the same electron momentum. Direct bandgap semiconductors are excellent for optoelectronic devices, as it can either absorb or emit photons much more efficiently. On the contrary, the group 4 element semiconductors such as silicon and germanium are all indirect bandgap materials. Thus, gallium arsenide are used in near-infrared, light-emitting diodes, and high-efficiency solar cells. For example, the Fraunhofer research team has recently achieved a record light conversion efficiency of 68.9% under monochromatic laser light with a new thin film photovoltaic cell based on gallium arsenide. A new property with compound semiconductors is the possibility of net electric polarizations due to the ionic character of the chemical bonds, as a result of the electronegativity between the anions and cations, particularly with the wurtzite semiconductors. In tetrahedral compound semiconductors, the group 5 and 6 elements form the anion. In other words, they are net negatively charged on the atomic site. On the other hand, the group 2 and 3 elements form the cation. The polarization implies a built-in electric field and a measurable voltage across the material in direction collinear with the polarization. The application of strain or force can further modify this electric voltage, thus allowing for the transduction between force and electrical signals. Such transducers is called piezoelectric materials, and aluminum nitride and zinc oxide are prime examples. Such piezoelectric materials find widespread use in today's mobile devices, such as surface acoustic wave devices for RF filters, microphones, haptic technology to future energy harvesting devices. As a matter of fact, nearly all applications that require the measurement of dynamic pressure change uses piezoelectric materials. Gallium nitride is another well-known 3,5 wurtzite semiconductor, which has a direct bandgap of 3.4 electron volts and find widespread applications in optoelectronics. For example, gallium nitride is the substrate which enables the 405 nanometer laser diodes used for discreting in Blu-ray technology. For the development of the blue light emitting diode, which enables efficient light and display technology, Akasaki, Amano, and Nakamura were awarded the 2014 Nobel Prize in Physics. Key to the breakthrough, besides its blue energy bandgap, is the good lattice matching with other nitride-based wurtzite semiconductors, allowing the seamless fabrication of heterojunction devices. Gallium nitride transistors can also operate at higher voltages and higher temperatures than gallium arsenide. Thus, they are also used in microwave power amplifiers. In solid-state lighting, illumination and displays technology, multicolor photodetectors, and on-chip spectrometer are enabled by semiconductors with different band gaps spanning across the visible spectrum, and sometimes encompassing also the infrared. This can be achieved by alloying gallium nitrides with a smaller bandgap wurtzite indium nitride, thus interpolating across the range of band gaps. Although there are many other compound semiconductors in the mix, the large mismatch in their lattice constant can pose issues with the integration of these various semiconductors onto a common substrate. Good lattice matching would allow for commensurate growth of the semiconductor layer, which otherwise would have to be either pseudomorphic or incommensurate. Accommodating the difference in the lattice constant in the latter configuration without incurring significant defects is an outstanding challenge in the semiconductor heterojunction field. Beyond these wurtzite and zinc blende semiconductors, the rock salt semiconductors are also well known for their wide range of electrical, optical, superconducting, and refractory properties. It exhibits a crystal structure like that of common table salt, sodium chloride. In these materials, the atoms are arranged in a cubic crystal lattice, with each cation being surrounded by anions and vice versa. They can be found in a variety of applications. For examples, rock salt lithium fluoride is widely used as optical materials in the ultraviolet due to its larger band gap. The rock salt magnesium oxide is used for oxide barrier materials, in tunneling magnetoresistance device, which is one of the key active component of the hard disk drive that we use in daily life. A huge class of outstanding photosensitive semiconductors are the perovskites, given by the ABX3 crystal structure, where A and B are cations and X are anions. X includes the elements oxygen and the group 7 elements as highlighted. The cations A encompass a wide range of diverse elements across the periodic table as indicated here. Same goes for the cations B as shown. Hence, perovskites is one of the most abundant structural families. Due to its unique crystal structure, some perovskites material exhibit ferroelectric properties, which can be utilized in novel nanoelectronics devices, particularly for memories. Ferroelectrics are a subset of piezoelectrics in that they also possess a spontaneous polarization in the absence of any applied field. Perovskites have also shown potential for high-performance solar cells, in conjunction with the promise of low production costs. For example, a perovskite on silicon tandem cell has a theoretical efficiency limit of 43% versus 29% for silicon cells. Are we done yet? Not quite. It is known that there are so-called van der Waals materials where the bonding in one or two crystal directions are mediated by weak van der Waals interactions. Graphene being a prime example, or the hexagonal boron nitride and the transition metal dichalcogenides. For the discovery of this class of materials and experiments that demonstrate field effect properties, Andrei Geim and Konstantin Novoselov were awarded the 2010 Nobel Prize in Physics. Previously, we mentioned that the group 4 elements are the only elemental bulk semiconductors. However, if we expand our horizon to include the van der Waals family of materials, we can find elemental semiconductors such as the black phosphorus and arsenic, which consist of puckered sheets stacked together via van der Waals interactions as shown. Such van der Waals materials also exist in the 1D analog. Most notable example is the chalcogen element, tellurium. It consists of a 1D chain of covalently bonded tellurium atoms in a helical structure with van der Waals interaction across the chains. Other chalcogens also exists in similar structure, such as sulfur and selenium, but with larger band gaps. Beyond elemental to compound van der Waals semiconductors, then we open the door to thousands of new semiconducting materials with band gaps spanning across the infrared, visible, and ultraviolet spectrum. These van der Waals materials is currently a hot topic of research in many fields, with new exotic properties being discovered almost daily. I believe we will have the opportunity to talk more about them in future videos.